This is the 7th video in our series on how to display video on the Commander X16. Let's just see where we are so far. So far we've recorded our source video at the resolution and frame rate we want. We've recorded our source audio separately and converted that into the 16-bit stereo PCM at the frequency we want. We've also divided that file up into files that are 1/20th of a second long. We've extracted all of our frames as 256 color bitmaps, and we've written the routines to load each image, load the audio file, and to load the palette file. So our next step is to convert the palette into a 12-bit palette that's compatible with Vera. So what we're going to do is, we're going to convert the palette. Let's just quickly bring up the program we've been working on. So LSRC is the subroutine that we need to load our source bitmap. It'll load whatever file is in file name S file and load it at 6FCC. So if we just go to S file and hit F5, we can see that it's image 0001. So we'll go back. I've also added another label here. It's Finny, and it's got the value of 0B32 in a word, and we've got 2,866 frames altogether, and you convert that to hex, it's 0B32. We'll be using Finny as the end value for our all of our frame numbers. So let's just go ahead and load our source up here. Okay, so that's loaded up the bitmap. If we go to 7000, you can see this is our bitmap. It's a blue value, a green value, a red value, and an alpha value. This is actually the palette for our bitmap, starting at 7000. Bring up the memory map here. We can see that the pixel data will be at 7400. So this is our palette data. We have to convert these 3 bytes into 12 bits. And we're going to round up. We're going to round up by comparing each of these values to F0, and if it's less than F0, we will add 8. So let's just go back here. Actually, let's go to some of the new code that I've written. First of all, there's init, and what this subroutine here does is just a very simple string. It loads 0 into the accumulator and then stores that in all the 0 page values from 60 to 6F. So let's just go to 0 page, and I'll hit F4 so you can see all of them. I've added a few variables here in 0 page, but calling init, what it'll do is set all of these to 0, and so the palette number will be 0, the video frame number will be 0. Here's the new ones that I've added. There's color, which is the color that we're looking at. There's dark, which is the darkest color in the palette. There is score, which is a score that we're going to assign to each color. All we're going to do is take the blue value, the green value, and the red value and add them together, and that will give us a score. We're only using 4 bits for each of these, so it's a value of 0 to 15 for each of those colors. So our total score is going to be some value between 0 and 45. And best is going to be the score of the darkest color. Temp 3 and Temp 4 I've also added because we're going to be using these 2 locations as an address pointer. We're also going to use Temp 1 and Temp 2 as an address pointer. So let's just go back here. The next thing we've got is GPLC. If we look at our memory map again, we can see we've got 2 palettes. We've got one palette at 7000 to 73FF. That's our source palette. And then we've got another one at 3E00 to 3FFF. That's the destination palette. That's the palette we're going to create from our source palette. So what GPLC does is, given a color stored in that 0 page color variable, it generates 2 addresses, one in the range from 3E00 to 3FFF. That address is stored in Temp 3, Temp 4. That's our destination address for that color. Then there's another one stored in Temp 1, Temp 2. That's an address in our source palette. So it's some value between 7000 and 73FF. And we can see that this is just a really short subroutine. So you've given a color here, it will give you two addresses in temp1, temp2, and another one in temp3, temp4. So xcall is about the longest one. This is the one that actually converts a color from the 24-bit to the 12-bit. So you need to have called GPLC before you call xcall. And what this does is, first of all, it loads the accumulator indirect with whatever value is stored in zero page at temp1, temp2. So that means it's loading the blue value from the palette. It compares that to F0, and if it's less than F0, the carry will be clear and we can add 8. This has the effect of rounding up. Then we shift to the right 4 bits and we store that at indirect at temp3, temp4. This is our blue value for now. And if we increment temp1, we're now pointing at the green value in our source palette with temp1, temp2. We load that value up into the accumulator and compare it to F0. And if it is less than F0, the carry will be clear and we can add 8, rounding it up. Then we end that with F0. That basically cuts off the low 4 bits. And if we add it to the value that's stored already at temp3, temp4, that's the blue value, we end up with a green blue value that we can then store in our destination palette. Then we increase temp1 again. That now means that we're pointing at our red source value. And if we increase temp3, then temp3, temp4 is pointing at our red destination value. So we load whatever's stored there at that address pointing to by temp1, temp2. That's our red value. We compare it to F0. And again, if it's less than F0, we add 8 in order to round up. Then we shift to the right 4 bits and store that in our destination palette. And that's all there is to that. So next, we've got xpal. Xpal is just a loop. It starts off at color 0, gets the palette locations for xcall and converts those colors, and then increments our color value. So when our color is FF, once we increment that color value, it'll become 0, 0 and will return. But until that point, it'll just increment and go back to here and do the next color. So I mentioned getting a score for each color before, and this is what this routine does. For every color, it just gets those palette locations in temp3, temp4. It loads up the one in temp3, that's the green blue value, ends with 0F to isolate the blue value and stores that in score. Then it loads up whatever's stored at temp3, temp4 again, that's green blue again. We shift it to the right 4 times and that just isolates the green value and divides it by 16. So now it's just a value between 0 and 15. We add that to our score, so now we have a blue plus a green stored at the score. Then we increment temp3, so now we're pointing at the red value in our palette. We load that value up, we add it to the score, and now we have a blue plus green plus red value in our score. Next, we have to find the darkest color in our palette, so we set color to 0, and we set the darkest color is also 0. We get the score for that color, and if it's equal to 0, then all we have to do is set the carry flag and we're done. If it's not equal to 0, however, we'll just store that score in best and we'll increment our colors. And as long as we haven't incremented all the way to 0, we'll skip this and get another color score. If we have reached 0, we'll just return with the carry flag clear. So if we haven't reached the end yet, we get a score, we compare that to best. Now if the carry is set, then that means our score is greater than or equal to best, and we can just loop back to our next color. However, if the carry is clear, then that means this is less than best. So we store our score in best, we load up our color value and store that in our darkest color pointer, and again we go back to incrementing our colors. So at some point we will leave this subroutine with a carry clear flag here, or we'll leave with a carry set if color 0 is already black. So Xpix I am not going to talk about this one just yet. I'll come back to that in a minute. cpal is finally the function that converts and saves that palette. So what it does is, first of all, it does xpal, which is the simple conversion, converting the 24-bit down to 12-bit. Then it calls gdark in order to get the darkest color. And if the carry is set on return, then our darkest color is black and color 00 is already 00. So we don't need to do anything further. We can just go to the end at 0D5B, which is spal, which is save palette. However, if color 0 is not 00, then we have to say, is it the darkest color? So we load up darkest color compared to 0. And if it is the darkest color, then we can branch ahead to 0D55 and explicitly set it to being black by setting the first 2 bytes of our palette to 0. If, however, 0 is not the darkest color, then what we have to do is swap it. First of all, we load the darkest color is already loaded in the accumulator, so we just store that in our color pointer. We get the palette location for our darkest color. We load whatever the green-blue value was for color 0, and we store that in our darkest color. And then we load the red value for our color 0, and we store that in our darkest color. And then, well, later on we're going to be setting color 0 explicitly to 0, but here's Xpix, the one I said I would talk about later. So let's go back to Xpix. And what this does is, if color 0 is not the darkest color, you have to go through the image and swap color 0 and the darkest color wherever they occur. So first of all, we set temp1, temp2 to point to 7400. And if we go back to our memory map here, 7400 is the start of our pixel data. And we load that value, whatever's in that pointed to by temp1, temp2. We're loading the accumulator indirect 0 page. We compare that to 0. If it's 0, then we have to change that to dark. So if it's equal to 0, it'll go down to here, it'll load the accumulator with dark, and then branch ahead to here where it stores that in the pixel data. If it is not equal to 0, we'll branch ahead to here where it compares it to dark. And if it's not equal to dark, we're not going to change it at all. But if it is equal to dark, then we'll load the value 0 and store that in our pixel data. Then we increment our pixel data pointers, and then we compare that to 08, or rather 8E80. 8E80 is just beyond the end of our pixel data in the memory map here. You can see it ends at 8E7F. So if our counters reach 8E80, we're done. So let's just go up here. Now I think I've gone through everything that I've written, and we are ready to test this out. All we have to do is set all those values in 0 page to 0 so that we are definitely saving the correct file, and we will convert that palette. So we've already got our bitmap loaded in memory. So if I exec test, then we can go into our Star Wars folder, and you can see that there's a new palette file, P000, and it is exactly 514 bytes. It's a good palette file. So that's it. That's how we convert a palette. On to the next video.